Hello everyone! Today we start a new chapter in our lives. Isn't that exciting? I'm sure you were probably tired of chapter 3, the graphing lines. So I noticed I kind of skipped ahead. It seems like we skipped a lot of material, but we wanted to make sure we cover this chapter first because it talks about lines and their graphs and using graphs of lines to do things. So kind of like while the graphs of lines are fresh in our minds because of this past chapter, we wanted to cover this material so it's easier and it's still fresh in our minds. For this section, this section, you're graphing lines, which might make you kind of annoyed because you thought, oh my gosh, I thought I left that chapter behind, graphing lines. So I think this section is more of an introduction to this topic, which is systems of equations in two variables. But in the coming sections that we'll see, there'll be better methods for how to solve these problems, and it will not involve graphing lines at all. It'll only involve algebra, which I like better. I much prefer doing algebra rather than graphing. So don't worry, this section is more, like I said, it's an intro, trying to give you the hang of it and I guess connecting two ideas, solving these systems of equations and the lines. They are connected, but we'll have a better way to do it. So just kind of bear with me in this section. It's pretty short and not too terrible, but we'll have better methods in the next coming sections. All right, so what's going on? What is a system of equations in two variables? Well, I guess in my mind, the idea is we've already looked at graphing a line, right? And then we remember way back when, in the beginning of the chapter, we said, oh, the reason that we graph a line is because, for example, if you see this guy right here, 2y minus 4x equals 7. If you graph that, that's a line. Or if you're trying to find all the solutions, remember we said there are infinitely many solutions. And the solutions look like ordered pairs, like x comma y. And since there are infinitely many solutions, it's impossible to list them all. What we do instead is just graph the line and we say, look at all the points on this line, x comma y. Those are all the solutions. I couldn't possibly hope to write them all out, but what I can do is, graph it and you can see, oh, look, those are the infinite many solutions. Great. So that was fun, but this whole chapter, it talks about, well, what if you have two lines? So the one I've boxed here, and then there's another one here, 2x minus 1 equals y. So there's two lines. Imagine you can picture two lines graphed on the same coordinate system. What we want to know, like it says here, is what's the solution to that system, and what that means is, what are the points that they share? Like if they intersect, where do they intersect? What point is on both lines? That's what we really want. We want to know what point is on both lines together. If there is one, sometimes there's not, but most of the time there is. You'll find one exact point where they intersect. So with that in mind, there's three possibilities here, and there's a picture of each. So if you plot these two lines, these ones specifically, I'm not sure what happens, but in general, when you plot two lines, they can either be parallel, like we've seen before, right? We saw parallel lines. Remember, that means those ones never intersect. They have the same slope and they'll never intersect. But if that's what a solution is, a solution to a system of equations is the intersection point. If the lines are parallel, that would mean, like it says here, there's no solution. This little symbol here that they wrote, it's like a 0 with a line through it. That's another way, just a symbol to say no solution. So we might see that. I guess if we try to find the solution of a system of equations and the lines end up being parallel, that means there's no solution. Because again, remember that a solution to a system is where they intersect. So if they don't intersect, there is no solution. Then another possibility, this is probably the most common one here. Most common is that you have two lines and they intersect somewhere. Like here, see, notice they have this intersection point here, x comma y. So that's more common. That just means they have one solution and you'll just list it as an ordered pair. Like say if the point was 3 comma 1, I don't know. That's the point they happen to intersect at. Then there's the solution, bam, one value. So far we see it's possible that there's no solution. It's possible there's one specific solution, something comma something. And the last possibility is, it could be that those are actually, you can't really see it in this graph, but wait, how do you even say that? Coincident? Nah, coincident sounds right. Really, just think of that. That means that they're the same line. They are the same line. Like if you graph them, they end up being right on top of each other. Like say, I'll try to do this. Let's say one's green. Okay, whoops. You graph it, and then you go to graph the other one. You say, okay, let me see. Wait a second. That's the same line. I just graphed the same guy. That would mean that they're the same line in disguise, which, if you think about it, okay, you graph the two lines. They're the exact same line. The solution to a system is where do they intersect? But if both lines are the exact same line, they intersect everywhere, right? Every single point is an intersection point. So that the last situation is interesting. There are infinitely many solutions. And you would write it like it shows there. We'll see this in an example, but you write it as they call it, they call this set builder notation. This means all the points that have this equation, mx plus b. And mx plus b will just be whatever equation you were given. Like say this example at the top, you'll say, oh, 2y minus 4 is 7. That's what you'll put there. That's just kind of a fancy way of saying every point on the line is a solution. Every point on the line is a solution. Just kind of the fancy math way of saying that. But okay, so that's kind of interesting, right? There's three situations, either no solution, one solution, or infinite solutions. So there's no way that two lines can intersect twice, for example. It's either never, once, or infinite times. Interesting. All right, let's see what we can do here. The very beginning of this section, we're just kind of getting used to it and, I don't know, just getting the hang of it. So we're not really going to solve these yet. We're just going to see, for example, here in part A, they give us a point and they're asking, is this ordered pair a solution or not? So what we have to do is we have to test this ordered pair for both equations. Ordered pair in both. So they give us two equations. I'm going to have to test it to see if it works in the first one and in the second one. In order for it to be a solution, it better work for both of them. So I'm going to try the first one first. We got x plus 5y equals 0. I'm going to replace the x and the y with the values of x and y from the point and see if I get a true statement or a false statement. So let's see, the x value of the point was -5 and the y value was 1. So if I simplify that, what's that? That's -5 plus 5, and that is 0, right? -5 plus 5 is 0? Check. Okay, but that's not enough. In order for this point to be a solution to the system, because system means both equations, I'd have to check it in the second one as well. I better check out for both or else it's a no-go. This is not a good solution. So I guess what did we just do? We just proved that this point, -5, 1, it's on the line, the one we just tested. So we've shown that it's on that line, but what we want to do is show it's on the other line as well. So we better try to test it in the other equation, y equals 2x plus 9. So of course I'm using the same values of x and y for that point. The point, x was -5, y was 1. I'm going to replace y with 1, x with -5, and then see if I get a true statement or a false statement. Let's see, so that's 1 equals -10 plus 9. Uh-oh, that's not true, huh? Because it's -1. Uh-oh. Nope. That means at that point, -5, 1 is not on this line. That means it's not a solution to the system. That's unfortunate. So be careful. I mean, we tested it in the first equation and we got, oh yeah, it's a solution. That means it's only on the first line, but we found it's not on the second line. So I don't know what these lines look like, but just for example, let's say one line looked like this, I don't know, and the other line looked like this. So since it worked on one line, that means it's a point on one but not on the other. So it's like this point here, for example. That is not a solution because what we're looking for is where they intersect. All right, so that's a no. The answer to that one is no. Let's try the next one here. So give us a point 5, 2, and they give us a weird, I don't like when they give us a and b instead of x and y, but I figured we might as well do one like this in case you see one in the homework or something like that. So if you're not sure, because usually it's x comma y, and I say, wait, if I have a and b, which one's which? Just think of it in alphabetical order. It must be a and then b, because the left one should be alphabetically first and the right one should be alphabetically second. So okay, I'm going to take that point and test it in one equation, see if it's true, and then I'll test it in the other equation and see if it's true. So let's see that. I always want to say the x value. The A value is 5, I'll replace that guy. And the B value is 2, I'll replace that guy as well. And I guess I could use parentheses, but I don't know if there's really a reason to. I mean, they're just adding and there's no negatives or anything. So I've got 5 plus 2, that's 7. Oh, that's true, 7 equals 7. Okay. So far that means 5, 2 is on the line, the first guy. But in order for that point, or that ordered pair to be a solution to the entire system, that point better be on the second equation as well. Or sorry, on the second line. So I'm going to try to replace that stuff. Put a... So what was A again? A was 5, that's right, 5. And then B was 2. So replace the A with 5 and the B with 2 and see what happens. You got 5 times 2 here, that's 10. Minus 8, that's 2. Oh, 2 equals 2, that's true. Alright, that means that the point I was given is also on the second line. On the other line, which was a 2a minus 8 equals b. Since it's on both lines, that means it is a solution. Yay! So the answer is yes. Yay! Because that means, like if you picture this, I don't know, we could use the same example over here on the left, this little picture I drew. Okay, think about it. What's the only point that's on the red line and the blue line? It's that intersection point, right? Any other point you think of is either on one or the other, but not both. So we did find the intersection point, or they gave us the correct intersection point, I should say. All right, looking good. Looking good. Okay, so now we know, if you have a potential solution, we know how to check it. Is it for sure a solution or maybe a solution? Okay. So now this is, oh, hello. The main thing is, think about it though. What if you're just given you're given the equation of two lines, like in example 1 here. I mean, where did they get this point? Did they just come up with that on their own, or so in most cases, we'll just be given a system of equations and we have no idea what a potential solution is or not. So this section, this is our method for figuring it out. See, notice example 2. They give us a system of equations, but they don't give us a potential solution. We have to figure it out on our own. So one way you could figure it out is this method in this section says just graph both lines. So maybe, how about I'll color code them so we can tell which one's which. I'm going to call the bottom line the green line and the top line the red line. So I'm going to take the top line, x minus y equals 1, and then try to graph that guy. So this is where you have so much freedom. I mean, you can try to, I guess in the last section we were graphing a line by finding the slope and y-intercept, so maybe we'll stick with that just to practice that. So let me graph this guy. Remember, if you want to graph it by using the slope and y-intercept, you have to isolate y first. Excuse me. So I'm going to move the x over, and then I'll have negative y equals, I'm going to write negative x plus 1. Then I almost have it if I just divide both sides by negative 1 to isolate y. Divide every single term by negative 1. And then I'll have y equals, well, a negative x over a negative 1 is a positive x, and then a 1 over a negative 1 is negative 1. So now that it's in that form, that's y equals mx plus b. I can identify, so the slope, that's kind of tricky though. The slope is supposed to be the coefficient of x, but it looks like there is no coefficient of x. But you think about a variable, it has an automatic coefficient of 1. Because you could always write this as 1x minus 1, because 1 times x is x. So it has a slope of 1, and the y-intercept 0, comma b, remember that's supposed to be 0, comma the constant term, which is negative 1. Okay. So we got the first, kind of all the information from the first equation down, and I said I was going to graph it in red just so we know which one it is. Red line, so I remember. Alright, so we're starting with, remember we have to start with the y-intercept, 0, comma negative 1, that would be here. And then, careful though, because I have a slope of 1. Okay, so I don't know if we've seen this yet, but remember, if you want to use slope, to graph a line, you're going to have to think of it as rise over run. But I don't see, it's only a whole number, it's not a fraction. But you know what? I can always make any whole number I want into a fraction by putting it over 1. So now I know I'm going to rise 1 and run 1. Both of those. Okay, so from that y-intercept I already plotted, I'm going to rise 1, and 1 is positive, so I'm going up 1. And then I'm going to run 1, And since 1 is positive, I'm going to go to the right one. So remember, up and to the right are the positive directions. And you know, I don't have a straight edge on my computer here, but these are problems where it's very important to make this line as straight as you can. And you know, I obviously didn't make it very pretty. But just try, because if you don't make this line straight, you're going to get the wrong intersection point. Because that's the point of these problems. I'm going to graph both lines, and I'm going to try to eyeball where it looks like they intersect and say, oh, that's the solution. Alright, so we'll try to do the same thing to the green line, graph them both together, and we'll try to eyeball where does it look like they intersect. So that guy's x plus y equals 5. If I want to graph that guy, I'm going to isolate y first, which wouldn't be too hard, huh? I just have to move the x over, and I'll be done with that one. So y equals, and I'm not going to write 5 minus x, I'm going to write negative x plus 5. And now that y is isolated, I'm ready to say, okay, the slope is, the coefficient of x is negative 1, and the y-intercept 0, b, 0, 5. Alright, but I'm going to try to do that in a different color so I can differentiate the two, a green. So I'll start with the y-intercept. 0, 5 is up here at 5 on the y-axis. And then the slope, I got to be careful because just like in the last line we graphed, I need slope to be rise over run, and since it's not a fraction, I'm going to make it a fraction by putting it over 1. That means the numerator, negative 1, is how far I rise, and the denominator, positive 1, is how far I run. And then rise is negative, that means I'm going down 1, since that's the negative direction. And then run is positive, so I'll be going right 1. So from that green point I just drew, I go down 1 and right 1, I'll end up here. Let me see if I can make this as a straight line. Oops, hello. Is that straight? Oh my gosh, I tried. So, and notice too, what if I had drawn one of those crooked, you know? I think it looks like I can tell what the solution is, but what if I get it wrong? So that's why you notice I wrote here, be sure to check your solution. And by that I mean, like we did in example 1. And we'll see, I'll talk about that more, but let's see, how about, where does it look like that intersection point is? Well, it looks like it's right above 3 on the x-axis, and it's directly to the right of positive 2 on the y-axis. So I think that's the solution. And then if you want to check it, check this point, 3, 2. You'd have to do like we did in example 1, where you substitute those values in here. The first equation, the red line was x minus y equals 1. The second equation, x plus y equals 5. But you know what? You might be able to do it in your head. So notice, if I replace x here with 3 and y here with 2, it's x minus 2 equals 1, which is true. So you might be able to check it in your head. I'll have to try it in the second one. The second one is x plus y equals 5. If I do that in my head as well, if I replace x with 3 and y with 2, it's 3 plus 2 equals 5. That's true. So I must have graphed it okay. I mean, I kept the lines as straight as I could. But for sure, if you make either of these lines sort of crooked or they slope a little steeper or shallower than they should, you're going to get the wrong answer. So be careful, check your answers on these ones, and use a straight edge. That'll make it so you probably will always get the right answer and you won't have to worry about it. All right, let's try this next one here. These last two examples, they're exactly the same thing. So you're just going to use whatever methods you want to graph these lines. And you know, in this one, maybe for fun, we'll mix it up. I'm going to graph the first line. You could keep using the slope y-intercept idea, but I don't want to forget the other method. So you can graph these lines however you want, and you'll get the right answer. But just for fun, I'm going to kind of remind us. Remember the other method where you find the x and y intercepts. So remember, you started off, you're going to let y equal 0 and find x, and then you're going to let x equal 0 and find y. So first thing I'm going to do, like it says, replace y with 0 and see what happens to x. 2x minus 2 times 0 equals 10. And what's x then? Then it would be 2x minus 0 equals 10. Well, that means 2x equals 10. And then I'll divide both sides by 2. Oops. And I'll have the x-intercept, x must be 5. Alright, so that's the x value of 1 point. So we know 1 point on this line. On the other point, we'll find, like it shows, now we want to find what happens when x is 0. So I'll take the equation 2x minus 2y is 10, but replace x with 0 this time, not y. So it'll be 2 times 0, but that's just 0, right? So that term just disappears and you'll be left with the 2y equals 10. And now I can solve for y completely by dividing by -2. And it looks like almost the same value, but now it's -5 instead of +5. Okay, so that must be the y value of the second point. That wasn't too bad, huh? So I'll plot those 2 points. Let's see, 5, 0, that would be here. And the other point, 0, -5 would be down here. Now try to make that line as straight as I can. Oh man, I should be using a straight edge, but, you know, do as I say, not as I do, you know, that kind of thing. Alright, that's as good as it's going to get, my friends. Okay. Let's try that on the other one. I kind of like that method for some reason. Although, you know what? Look at this guy. We can mix it up if we want. This guy is like, he's telling me, man, it's really easy to get my y by itself. I can use the slope and y-intercept. That's true. See, I guess that's the beauty of having more than one method to, to graph a line. It's like in different situations, like in this one, it looks like y is really easy to isolate. So I might as well use the slope and y-intercept. But if there's an equation where you say, you know what, getting y by itself looks like kind of a pain, I'll just use the like we did in that last part where we found the x-intercept and the y-intercept. So you can mix it up if you want, use exclusively one method and never the other, or you can sometimes use one and then never the other, whatever. Oops. All right. So looking at this guy, the slope will be the coefficient of x, which is 1. Since there's nothing in front of it, it's automatically a 1. But again, I want to think of it as rise over run, because you can only use the slope to graph a line if you see a denominator. But you can put it over 1. You can make anything a fraction by putting it over 1. All right, so I know I'm going to rise 1 and run 1, and then the y-intercept 0, b. That's 0, the y-intercept there is that constant term 5. Okay. So I'm going to plot that point. This will be the green line. I'm going to plot that point 0, 5. Where's that guy here? He's up here. Okay. And then I'm going to rise 1. Okay. Rise. Remember we said it's misleading because rise could mean up or down. But since it's positive 1, I'm going to go up from there. Up 1. And run, it's also a positive 1. And then on the left-right direction, the right is the positive. So I'm going to go right. So from that point 0, 5, I'm going up 1, right 1. Kind of just went a little diagonal there. Oh, look at that. Interesting. Oh, that is not a straight line, my friends. Pretend like that's a straight line. Oh my gosh, this is so bad. Okay. And you know the way I drew these guys, I'm thinking, okay, these might have been meant to be parallel. But the way I drew them, they kind of look like they're further apart at the top right than they are at the bottom left. But I think you know they're parallel. If they don't intersect on your little tiny screen here, then they're probably parallel because they're going to make these problems work out nice. Yeah, so if you don't see them intersecting on your screen, like, you know, this little tiny grid I have, this 10 by 10 grid, then, they're not going to intersect at all. These must be parallel. And, you know, if you've kind of forgot what that means, remember up at the top it said, what happens if they're parallel? Let's see. Where were they? Here. If they're parallel lines, that means there's no solution. So all that work, and there's actually no solution. Isn't that nice? Oops, sorry. So I'm going to say no solution. Again, remember, when you're solving these systems of equations, what you're looking for is where do they intersect? And if they're parallel, they do not intersect ever, so there's no solution. Oh, that's disappointing, huh? Oh well. All right, next one. Our last one, actually, huh? Try not to be too sad. Let's graph this guy. 2x minus 3y equals 6. All right. Let's look at that guy. And that one, to me, I look at that and I say, getting y by itself is kind of a pain. I'm just going to make that little table and find the x and y intercepts. But, you know, if you like the slope and y-intercept like we did in this last example, you can just always stick with that. But you know what? This is my tricky trick, you guys. Check this one out. Okay. The first thing I'm supposed to do is replace y with 0, right, to figure out what this point is. But you know what? just picture that. What if y is 0 here? What would happen? That'd be 3 times 0, which is 0. So all you'd be left with is 2x equals 6, right? Is that true? Yeah. If you put a 0 for y, 3 times 0 is 0. That whole term disappears and you're just left with a 2x equals 6. And then you can divide by 2. And that was pretty easy, right? You could actually do that all in your head if you wanted to. Not too bad. Maybe we could try the other one in our heads. Now this one, we're replacing x with 0. So picture this guy, 2x minus 3y equals 6. All right, what if this x was a 0 here? 2 times 0 is 0. So that whole term is gone. Now just picture what's left. Negative 3y equals 6. If I want to isolate y, I'll divide both sides by negative 3, and I'll get negative 2. But if you want, you can actually write it out, just to be safe. But just keep in mind, it's not too bad to find the x and y intercepts. A lot of times you can just do it in your head. So that term would disappear, then you would divide by negative 3. That's how you get the negative 2. Okay, so it's not too long, right? I feel like I did all that in the same time I could have solved for y and identified the slope and y-intercept. Okay, so those 2 points, what do we have? 3, 0, that would be here. And the other point, 0, negative 2, where's that guy? Here. All right, let me connect those guys. Gosh, I wish that was a straight line. Oh well, let's try the other one. 3y minus 2x is negative 6. It's a good song, huh? So, doesn't really matter, but I'll do the same thing. I think it just seems easier, quicker. All right, you want to try to do this one in our heads? Let's try it. You could write it out, but I think it'd be kind of silly. So, all right, I'm going to focus on y equals 0. So just picture that. What if y was 0? Here's y right here. 3 times 0 would be 0. So all you're really left with is negative 2x. Negative 2x equals negative 6. If negative 2x equals negative 6, you would divide both sides by negative 2, and you'd get negative 6 over negative 2, which is 3. I think so. And if that's kind of too confusing, you can just write it out. Actually replace x with 0, but don't feel like, actually replace y with 0, but don't feel like you have to. But if that guy is 0, then all that's left is negative 2x equals negative 6. And then you would divide by negative 2 and get 3. And there you go. Okay. Now let's try the other one. Now what if you take that same equation, x equals, okay, but this time I'm replacing x with 0. Okay, so just picture this x equals 0. Then it would be 2 times 0 sitting there, which is 0. So all you're really left with is 3y equals negative 6. If you divide both sides by 3, you're left with negative 2. And there are your 2 points, and you didn't really have to write anything out if you didn't want to, because you could do all that in your head. But if you want to write it out just to be safe, that's not a bad idea. I'll replace x with 0, then what's left? 3y, 2 times 0 is 0, so that's gone. 3y equals negative 6. If I divide both sides by 3, I'm left with negative 2. There we go. All right. Oh, you know what? I was so wrapped up in all that. Look at those 2 tables. Those 2 tables are the exact same thing. Look at this guy. 3, 0, 0, 2, or 0, negative 2. 3, 0, 0, negative 2. What the heck? So, of course, if I plot those points, it's going to be right on top of the other one. And I'll connect those dots. Okay, these are the exact same line in disguise. Same line. What kind of bull crap? Okay. That's crazy. Okay, and remember up above, in the very top of the first page of the section, it said that when they're the same line, that means you're going to have infinite solutions. Because what you want is, where do they intersect? And since they're the exact same line, they intersect everywhere. Every single point on every single point on the line is a solution. But the way they want you to write it is this interval notation. This set builder notation. So it always looks like this, and all you have to do is, next to these this colon or these 2 dots, you say, just put the equation of either line. Since they're the same line, it doesn't matter. So I don't know. You can look back at the original guys and say, which one do I like better? Yeah, the top one. Why not? 2x minus 3y equals 6. So this is your real solution. It's infinitely many solutions. That's just, again, this is a fancy way of saying all the points, x, y, such that they satisfy this equation, or pretty much all the points that are on this line. That's kind of a fancy way of saying that. All points on the line, blah. Okay, but if you do the homework, you'll see them write the answer like this. So just so you know what they're doing, that's what they're saying. They're saying that's infinitely many solutions. Oh, so I know this method doesn't seem great, right? Like in this, especially that example 2, I think it was. I said, what if I were to draw those 2 lines crooked? Then I wouldn't find the right solution. I would have got the wrong one, and this doesn't seem like a very mathematical method. You know, math is usually very exact, and it'll always work, and you always do the same thing, and there's not a lot of guesswork. So this isn't the best method. I think this is just a method in this section just to give us an idea, to connect the dots between the fact that these are lines and you want to find where they intersect. But in the coming sections, we'll actually have 2 different methods on how to solve a system of equations, and if this will probably make you happy. You won't have to graph a line in either of them. It'll be all algebra. People usually like it a lot better than graphing lines. So look forward to that. I'll see you soon in those sections. They'll be a lot more fun. No graphing at all. Hopefully you like that, and if not, sorry if you miss graphing. But thanks for paying attention and graphing lines with me. Hopefully it made some sense, and I'll see you in the next video. Thanks. Bye.